thank you so much for being here. It's really thrilling to be speaking to a big audience, like tonight. Like Matt said, today will be a very short journey to the stars, trying to understand why we care about stars, what do stars do, their lifestyles, how they live their lives, trying to understand a little bit their body language as they evolve and they live their lives. A little bit about me first. I work here. Is this right? Oh, excuse me. No, this doesn't work. Never mind, I'll just use this. So, I am an astrophysicist. I work in space science here at the Institute. I also tell stories about space and about the research that I do. I will tell you a little bit more about that at the end. Before we start this journey, let me ask you a quick question. Are you all comfortable? Yeah. Can you all hear me well?
Yeah.
Anybody feeling too hot, too cold? I don't want any barriers for listening between us two. I want you to be able to be fully present today. So we're all good, yeah?
Yeah.
Great. Before we start talking about the stars, let me ask you a question. I have been studying stars for a PhD and now as a postdoc for about 8 years. The question is, why should we care about stars? Most of you here are taxpayers and your pocket funds my research. Why should we care about something so distant as the stars? Thank you. So, why should we care about the stars? Can you give me ideas?
Because you're awesome.
Sorry?
Because you're awesome.
Because they're awesome.
Awesome, of course! In their own right, they're awesome for their own right, yes.
Because we've been curious and want to know a lot of things.
Brilliant. We are innately curious. And this is how we progressed as a civilization, right? We're curious, we want to know. Brilliant. What else?
Because we're made of stardust.
Exactly. We're made of star stuff. What else? Yes?
Because our sun is a star.
Exactly. Our sun is a star and the sun powers our lives. Right? It defines when we wake up, when we go to bed, when our day starts, when it ends. It defines our activity. It helps produce the food we eat. What else? Do you ever think? Any other questions? Yes, answer.
Why not?
Well said. Why not? Because we can. Do you ever think, are we alone in the universe? Is life as we know it special and unique? Or is there life elsewhere? Do you ever think of that?
Yeah.
You do. One of the reasons we need to study stars is that stars host planets. And we know now that every star we see out there has one or multiple planets. You can imagine the number of planets out there. And we cannot but think, with all this massively this sheer number of planets, one of the planets could host life. And we think, these planets that we see, are they tucked under a stable atmosphere? Can they support life? Do they have a biosphere? Is there life there? Or are they torched by the star's activity? They're barren lands that cannot possibly hold life. To understand the conditions a planet is in, we need to understand its host star. The star will provide life for this planet. And you know that when a star is born in its massive cloud, it has a disk around it, a disk of matter, where clumps of material are churning around it. Yeah? And these chunks of material, chunks of matter, go around and around, and sometimes they collide, they stick together, forming bigger chunks, which still go around, collecting other pieces, until you have a nice mature planet, which goes on clearing out its traffic lane, and then a stellar system is born out of this chaos. So what hosts this planet is a star, and to understand the conditions this planet has formed in, and the conditions it exists in, its environment, we need to have a better understanding of the star. That's one reason. In the darkness of the universe, stars are beacons. They're visible probes. When they're sufficiently evolved, they can be really bright. We can see them in our galaxy, as well as outer galaxies, millions of light years away. Because they're bright, they allow us to probe the structure in the universe, in the environments they are born in. Like you see here, this globular cluster studded with stars of different colors, evolving, doing their own different thing, depending on what stage they are. They're not only the visible probes, but you know that the stars are the throbbing heart in the universe. They drive the most rattling events in the universe. They're the source of energy. They provide energy, they energize their host environments. What you see here is a star that's quite elderly, and when it's an aged star, it rips itself apart. It ejects this outer stellar matter into the universe in very fast and energetic wind. So all the material that has been produced in the star is now being ejected into the universe, and this will form new planets and new stars one day. It's a source of energy, and it's also a source of radiation. In the Rosette Nebula you see here, these are blue stars. They're hot, they're very hot, they're very massive, and they eject winds at immense amounts of energy. They excavate their regions, they hollow out their regions. And this radiation they're spewing out compresses the gas that is loitering around, heating it up, driving the star formation. So you see, stars weave this tapestry of creation and destruction in the universe, simply because they're immense and very energetic. You know that one of the fundamental laws of physics is that when a charge moves, it creates a magnetic field. Now, stars can create a magnetic field. How? You know that a star inside the star, this is a video from our sun. Inside the sun or inside the star, the atoms are stripped of their electrons, some or most of their electrons. And what you end up with, the soup you end up with, is a positively charged atom or an ion and a sea of negatively charged electrons. And everything is moving and turning around, and when charges move, they create magnetic fields. And these magnetic fields, in turn, make a force on any charged particle. So on the surface of the sun, for example, we have the stellar material that is charged, and the magnetic fields will create a force on these charges so they can levitate them above the photosphere, and this is what you see as a solar flare. There's a stream of stellar matter following the magnetic field lines like ants on a thermal trail. And this is why stars are threaded by magnetic field lines. They are created inside the star because of this turbulent motion of charges. One of you said that we are made of stellar stuff, of star material. And it's true. Stars have created all the elements in the universe except hydrogen. at the beginning, the Big Bang created the hydrogen, some helium, and traces, sprinkles of lithium. Everything else has been the making of stars. Here you see the periodic table. Different elements are created in different environments, different stars. Some are low mass stars, some are massive stars. Everything you see, the iron, the gold, the silver, even the carbon and nitrogen, oxygen that make our own bodies, they are formed in stars. I think this is the most significant gift astrophysics has given humanity. It's telling us, humans, that we have a cosmological connection through the stars. There's stellar lineage in our own DNA, and this is a very profound connection. Now, having talked a little bit about why we should care about stars and why they're important. When we gaze at the night sky, this is by no means what you see, but I'm getting somewhere. You see stars of different colors, yeah? I mean, on a particularly clear night, you can pretty much sometimes tell that a star is blue or red, like Betelgeuse, for example, you can see it's reddish. Rigel is blue. The sun is yellow. We've got white dwarfs as well, and we have red giants, we have blue supergiants. Now, what's the connection between these? Why do we have different colors? Are they different stars? Is it that a star can be red, or can be blue, or can be white?
It's different wavelengths of light.
Exactly, but why do they have different wavelengths?
Because they're different distances.
Not just distances, yes.
Because they're younger or older, and when they're younger they're more active.
Brilliant.
When they're redder they're colder and less active.
So are you saying it has to do something to do with age?
Yes.
Exactly. Now, do you know that what you said now, it took us 50 years to figure out? See how smart you are?
No, but what I do know is that a lot of discoveries have taken 200 years. Or way more, like
That's right. 200 years and even more, and there are things we still don't know. So back in 1900s, in the Harvard Observatory, people were observing stars, and most of the people, there were people working on classifying stars of different types. And the people who were working on these classifications were mostly women, because back then it was considered inappropriate for a woman to be operating a telescope or be out late at night on a telescope. So women were delegated lab work or office work, and most of the very famous figures in the world who have done classification of stars, women, they've classified hundreds of thousands of stars. We could tell that these are different colors, different types, and the answer waited 50 years to discover this, that it's actually a journey, it's an evolution, it's an evolutionary process. What you see in this figure is the time axis going to the right, and here you see stars of different masses, born with different masses. The very low mass stars that do not manage to shine, to burn their fuel and shine, we call them the failed stars, or the brown dwarfs, and they live extremely long times. They're very boring stars as such, they don't do much. If the star is close to the mass of our own sun, it lives its life, most of its life, stable as we see it now. Then eventually it will become a red giant, and I'll tell you why later. But this actually we have established now. After it becomes a red giant, a bloated red giant, it eventually loses its envelope as a planetary nebula, while its throbbing heart just is left as a naked white dwarf that is left to cool down as it evolves. And these planetary nebulae have nothing to do with planets. Yeah, it's just an unfortunate naming, I would say. They're one of the prettiest objects you could observe. Now these are false colors assigned by telescopes for radiation we can't really see, but they're very, very, very pretty structures. Now, if a star is slightly more massive, it can become a blue supergiant, then a giant. It can explode as a supernova. And all these processes, as stars evolve, they start from a cloud, evolve, and then shed their material back into the universe. They donate it back into the universe where new stars and planets would form. It's a cycle. Now, you see we have different stars, different types of stars, different evolutionary phases. But it's not a random zoo of stars. There's a standard classification that we have now established. Before talking a little bit about how we classify stars, let me do this experiment with you. In this room here, if I try to survey you, and I say, okay, on this graph, I've got the height, your heights here, and your weights on this axis, and your weight would increase if we go to the left. If I get the data for each and every one of you, how do you think it would look like? The data would look something like this, with this main band in the middle. The main band increases as we go to the left, and this is simply saying that as the weight of the person is bigger, generally speaking, this person is taller. Okay? This is what the graph is saying. Now, of course, you can see some exceptions. On the upper right, you can see some people who are very light, that do not have a big weight, and they're very tall, so very tall and thin. And on the bottom left, you can see people who have big weight and are short in height. Okay, so there are these exceptions. Kind of similarly, we noticed a relationship between the stars, but between their brightness and their temperature. We see kind of the same relationship. If the temperature goes to the left, it increases as we go on the graph, to the left, as this arrow shows. This says that, generally speaking, the hotter the temperature of the star, the more bright it is. And this main band that you see here is called the main sequence. And stars generally, on the main sequence, are extremely stable, and they live most of their lives on the main sequence. About 90% of their lives, they live stably on this sequence. And as you go up, the mass of the star is increasing. So stars of higher masses occupy higher, have higher luminosity and high brightness and higher temperature. Okay? So this is increasing mass. And the sun is just here. And just like humans, there are, this graph, by the way, was created by two people independently, the Danish astronomer Henry Einar Hertzsprung and the American astronomer Henry Russell. And this is what we call the Hertzsprung-Russell diagram. Just like the figure I showed you about humans, this also has exceptions. You can see the stars here and here. These are the giants, the red giants, and these are the white dwarfs. Now, I have a question. I said that if the temperature is high, or for very bright stars, their temperature is usually very high. These stars, however, are very bright, but their temperatures are low. So they are very bright, but they have low temperatures. Can anybody tell me why? What makes them so bright if they're relatively cold?
Lots of surface to radiate from.
Exactly, a big surface area. The surface of the star is so big because it's bloated that it radiates, it's very bright. What about these guys here? They're very hot and yet they're not very bright. Yes?
Because they have litter surface area.
Exactly. It's the opposite because they're very small. A white dwarf is the size of Earth. So it's very small and so it's not very bright. Now what is this figure telling us? Why have I spent time explaining to you this figure? This figure is important because if we observe a star, it's like a fruit fly observing us. If a fruit fly is observing me, it does not live long enough to see me grow from a child, get a PhD, come to Cambridge, get married. It cannot. It doesn't live long enough. Now, when we observe a star, we don't live long enough to see the star change from being a main sequence to a giant to a white dwarf. So how can we tell that our sun will eventually become a red dwarf, a red giant, and then eventually a white dwarf? When we look at the stellar community, just like I look now at you here, for the young members of the audience, if we look at the parents, we see the parents are musicians or architects or lawyers or scientists or engineers or bus drivers. And then we can expect that, even though we see the younger people here and during the talk I will not see you age, I know that eventually when you grow up, you will become lawyers and musicians and artists and scientists, etc. So I can predict what will happen to the young people in the group by seeing their parents. This is saying exactly the same thing. Because in a stellar community, the star that is more massive will age faster. By looking at what's happened to the very massive star that has become already a red giant, we know that given time, our star will become a red giant. So this is a tool to predict the evolution of stars given time. And this is one of the essential tools in astronomy. It's predictive. It has predictive power. Now, in our neighborhood, 97% of the stars are main sequence stars. About 10% are white dwarfs, and less than 1% are giants, because the giant phase is very fast phase. So stars evolve very fast through that phase, and not many stars are giants. Now, as they evolve, what do stars do? How do they sustain their life? This you've probably seen before. You know that a star is remarkably stable during most of its life. What is keeping the star together, this massive sphere of gas, is gravity. It's under its effect of its own gravity. Now, to be able to, not to contract, it's pushing back. For a star to be stable, there must be something pushing back against gravity. And what's pushing back against gravity, we know, is the pressure. Now, what is causing this pressure? Yes?
Elements.
What's happening to the elements?
Yeah, bursting out.
They're fusing and they're burning. Yeah? So now we know that in the heart of the star, at the very core, there is a fusion of the chemical elements producing this energy, this pressure, and sustaining the star, making it stable most of its life. And where is the energy coming from? You've all seen E equals mc squared. This is one of the most photogenic equations that we have. In the center, on the heart of the star, matter is being transformed into energy. This is the equivalence between energy and mass. Yeah? It's like a conversion, like you're converting pounds to dollars. Mass at the heart of the star, this is telling us how much the massive energy that is locked up in mass, in matter, and matter gets transformed into energy, and this is what sustains the star. And for example, this star, like our own sun, made mostly of hydrogen, about 28% helium, and the rest of the elements. The core of the star is burning from hydrogen to helium, so eventually we get a helium core, but nothing is really happening in the envelope. There's no burning in the envelope. It's largely non-burning. So what's happening as the star evolves? You know that material is burning at the center. At some point, the material will run out, right? If it's burning hydrogen, it will run out of hydrogen. So what would happen? Remember that this fuel is sustaining the balance between gravity and it's holding it against gravity. So when the fuel runs out, gravity wins over and the core contracts. Now when it contracts, it heats up and this energy seeps through and it heats up the shell around the core that still has some fresh hydrogen. Okay? Now what happens next is that the rest of the star would expand into giant dimensions. And when it expands, it cools down, so it becomes red. And when it cools down, we start having very large-scale turbulence in the envelope of the star, huge mixing. You can imagine it like a chef mixing soup in a pot, yeah? Or a giant dog's tongue lapping up material from the surface to the center. So this motion mixes up whatever was created here by the fusion to the surface. And this mixing, material is hot, it rises, it cools down, and it sinks. And this is what we see at the surface of the sun, for example. Material cooling and rising. It looks a bit darker than the rest because it's cooler, not cold, just cooler. And then it sinks, and it heats up, and it rises back up again. Now, a famous scientist, Erika von Vitens, provided the theory that we use now to model this mixing. And this is a very important phase in a star's life because its surface composition at this point changes. So when we observe a star, the star would be very proud of this phase of its life because its surface abundances have changed, its surface composition changed, and what is equivalent of a star's photo? If a star is on social media, its photo would be its spectrum. Okay? The spectrum that we see when we look at a star with a telescope, we see these dark bands that look like a barcode, which tell us about the composition of the star. Maybe it's hydrogen, has helium, has calcium, etc. And these correspond to the dips in light at each particular wavelength. And this is just briefly, you probably know this, that when light shines through a prism, we get the constituent colors of the white light, the rainbow colors. Now, when light passes through the atmosphere of the star, which has different atoms, these atoms are hungry for light, and they have particular tastes. They pick up specific parts of the spectrum, and whatever they pick to eat or absorb goes missing, and it becomes black. And these atoms eventually re-emit this radiation in different directions, which we cannot probably detect, and this is called the emission spectrum. And this is what we actually see, these dark bands, which tell us what's been produced inside the stars. Now, the atmosphere of the star is enriched with elements that have been fused in its factory, in its core. And then as the star evolves, when it becomes very expanded, its outer layers are less bound to the star, and they get lost into the interstellar medium, as you see here. And this is the material that's rich in freshly processed material, goes into the environment and or the medium between the stars, the interstellar medium, and forms new planets and stars. This is the fate of our own sun. The sun will become a planetary nebula. It will rip itself apart. Its envelope will be shed off. It'll look as glowing rings of gas, while its throbbing heart, the naked white dwarf, will be left to fade and die. This is the end phase of a star's life, as this beautiful planetary nebula. This is a cat's eye. this glowing rings of gas and the white dwarf at the center, the Helix Nebula, the Saturn Nebula because it looks like Saturn, Eskimo, etc. I hope this has put a little answer to your wondering maybe if why we care about stars. Before I leave you, I want to mention to you Shahrazad Speaks Science. When I go to give talks, people are very interested in astronomy. They want to know about the stars and the galaxies and the planets. And I noticed that people wish to know more and read more. So I created Shahrazad Speaks Science. You can find it at shespeaksscience.com. Shahrazad is a storyteller from 1001 Nights. I don't know if you know the story, but Shahrazad is the storyteller who keeps her audience engaged by telling them a story and leaving it at a cliffhanger so that people would know more. And this is why she keeps telling stories and stories for 1001 Nights. So Shahrazad Speaks Science, you can find us on Twitter and Facebook. Please do follow us if you like the story. You can go on stories here. You click on stories, you find the stories I have so far. When I talk about how starlight has helped us navigate traveling the land and the seas, and now it helps us navigate the galaxy and our knowledge of the skies. A journey from your backyard to the stars is in there. And here I talk about the dietary requirements of stars and why we see these dark bands in the spectrum if you're interested. And I also have other scientists contributing. You can also read their articles there. And our latest is a professor from Chile who used to work here, Paula. She uses Darwin's principles of evolution to track the lineage of the stars, the pedigree of stars, using their chemical abundances as their DNA. So, if you like this, you could just click on subscribe, fill in these few details, click on submit, and you get an email when a new piece is out, so you don't miss out on anything. My next article I'm writing is about binary stars and their interactions as a couple. And then you get a newsletter about the latest piece, and then you could just read it in your own time. I hope you found this useful, and I'm happy to take your questions. Thank you.